Okay, I think we're recording now. Okay, so today I want to finish up some of the material on stochastic simulation, and let's see if we can focus that. So, so in stochastic simulation, the idea is this: that you have some. Well, why is that hunting? Autofocus. Why is it hunting? There it goes. Okay. In stochastic simulation, the idea is that you have some probability distribution problem. Would like to generate a random variable from distribution P of X. Okay. So the problem is, if P of X is some complicated distribution, it's not something you can look up in a book. I mean, in the so if X is if X is a member of R, right? Then what you would do is you compute. You'd have like f of X, fx of say t is equal to the probability that X is less than or equal to t. Okay, so that's the cumulative distribution function. You calculate the inverse of this, which has to be done in a particular way. But if this probability distribution doesn't have any jump discontinuities in it, it's relatively straightforward. So you take you have if f inverse of X of something, I don't know, which I'll use another letter. I'll call it U. Okay. Okay. So this is the inverse CDF. Then what you do is you generate a random variable, a uniform random variable on 0, 1. And last time we spent a lot of time talking about how you can construct a uniform random variable on interval 0, 1. It's but I remember the answer was that you just if your probability distribution, if you measure your probability space is the interval 0, 1, it's just the function omega. Anyway, in a computer, if you're doing this with pseudorandom numbers, what you do is you generate a pseudorandom variable that's uniform in the interval 0, 1, and there's a lot of background on how to do that effectively. Okay. So then what you do is that you generate then X is equal to F inverse X of U, where this is uniform random variable on 0, 1, right? Okay. So what's the problem? Okay, there's only a few victims out there, so I'm going to see if I can get somebody to answer. I'm recording this, okay? So you can write as a chat if you feel embarrassed to answer, or uncomfortable, I should say, answering verbally, but I'd like you to answer. So what's the problem with this? The problem is that, trying to get used to this. What's the problem with this? Not always invertible. That's true, but it's true that it's not always invertible. But if we go back to problem oh, I can't, problem 2, there's a formal mechanism for how you can invert it. It's not that it solves the problem. I mean, it's not like a general inversion, but hold on. Problem 2, the infamous problem 2. Let's see if we can go to problem 2. Okay, so the solution is, in the general case, you have that F inverse of X, right, is equal to, we'll say of U, is equal to the infimum over the set of T, a member of R, such that f x of T is greater than or equal to U. So this has the desired properties. The problem comes in when you have like a discontinuity in F. So if this is like f of x of T, x refers to the random variable x, and then what happens is that if you have a discontinuity, so it goes like this, and then at this point it's like that. So that means that there's a finite probability of taking on that value. Say this is 1, okay? And so how do you invert that? So this handles it properly, okay? So I won't worry about it. So the discontinuity thing isn't so much of an issue. You can work around that. That's what problem 2 is. But so what's sort of the practical issue? The practical issue is that computing the inverse might be extremely difficult. Like it might have a very difficult, complex form, right? Especially if this is a real, this is a random variable, so it's a one-dimensional case. But if you have a multi-dimensional case, it's horrible. So in general, that can be difficult to do. Okay, so so the question is there a kind of a more practical way of generating random variables with a specified distribution? So here's how you do. We have this thing called the Metropolis algorithm. Okay, so the first thing you do is this. You generate a proposal. So first of all, it's going to be, you're going to repeat, because this is going to be a repetitive thing, and you're going to start off with you initialize x, okay, and then what you're going to do is from x you're going to generate a proposal. So you're going to generate an x prime with some distribution, which is going to be, I think I used the letter Q. Let me check that. All right. Yes, Q. Okay, yeah, it's Q of x prime given x. Okay, so this is generate a new random variable x prime according to proposal distribution Q of x prime x. Now it's going to turn that this proposal distribution has to have certain properties. We'll worry about that later. Then what you do is you say, okay, so you take this new thing, x prime. So if if, okay, you first calculate delta E. Okay, oh, hold on for a second. I skipped one thing. What you have to do here is you say, okay, express step 1. Express P of X in the form P of X equals, say, 1 over Z exponential of minus U of X. You'd say, well, so can you always do this? No, you can't do it if P has probabilities that occur with probability 0. But if you, so if the support of this distribution is a function, it changes, okay, well, no, right, is, if there's some states that occur with probability 0, then you just have to eliminate them from the state space, okay? Because you can't take you can't take the log of 0, because U of X equals the log of P of X, right? Okay, so, but subject to that concern, you can always do this. So right, so I'll write that up here. We'll have that P of X equals 1 over Z, where Z could be any function, any constant, times, oh gosh, 1 over Z exponential of minus U of X. Okay, so delta E then, this thing is called the energy. Okay, so so what you do is you compute delta E, E's for energy, and that's equal to U of X prime minus U of X. So it's the change in energy. Now, if the energy goes up, that means the probability has to get lower, right? Because E to a negative number becomes smaller. So if the energy goes up, the probability of the new proposed state and the old state, the probability of the new state has got to be lower than the probability of the old state. So if the energy goes up, okay, if the energy goes down, then if the energy is negative, delta E is negative, then the probability of the new state's higher. Okay, so if delta E is greater than or equal to, if delta E is less than or equal to 0, then what you do, then what happens is that you just set X to X prime. You accept the result. If delta E is greater than 0, so if the probability goes down, okay, then what you do is this. You first generate, then with probability P equals E to the minus delta E, you set X to X prime, and otherwise you do nothing, or retain state. Okay. So I don't know, maybe this looks more complicated than it really is. There's really two, what do you do? So first of all, this is the probability. Let me just do this one more time. So the probability of X is 1 over Z times E to the exponential minus U, okay? So the first thing you do is you generate proposal. And the proposal is x prime is q of x prime given x, according to some distribution, okay? 2 is compute delta E equals u of x prime minus u of x, okay? And 3 is accept, reject. So you accept or reject the proposal. This is actually the only part of the algorithm that's a little tricky. Okay, if delta E is less than 0, so if the energy goes down, you accept. If delta E goes up, you accept with probability P equals e to the minus delta E. Now, as delta E gets larger, and then you repeat. As delta E gets larger, then the probability of accepting gets smaller. So you'll mostly reject if this delta E is very large, okay? So, right, now, yeah, now there's an additional constraint, one more thing. We need that q of x prime given x equals q of x given x prime. So the proposal distribution has to have this symmetry property. What's the intuition behind that? The intuition is that if it doesn't have the symmetry property, what can happen is that, let's say you have 2 states, okay? You have 2 states in your system. This is 0 and 1, okay? So if you always proposing that if you're in state 0 that you should go to state 1, right? So you're always saying, oh, I want to go there, okay? And then, but when you're in state 1, you still propose that you're in state to go to state 1. Well, you're never going to propose, it's going to be asymmetric. You're going to tend to always going to go to state 1 because you're always saying, oh, let's go to state 1. It's the analogy I like to give is that you're trying to go out for, you're going out for dinner, okay? And like, I don't know if you've ever had the experience of having a bunch of people in the car and you're trying to decide where to go to dinner. So, you know, one person wants to go to a pizza place, one person wants to go to the, I don't know, Chinese, another person wants to go to, you know, Italian, right? Now, and then like, okay, so you want to have like a fair distribution, okay? If one person always says pizza, 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 and you know, no, I don't want to go to pizza. Pizza, no, I don't want to go to pizza. Pizza, no, I don't want to go to pizza. Then if you ever accept the pizza, well, you're going to go to the pizza, okay? So in that case, it would be like unfair because you're constantly proposing pizza, so it's getting a disproportionate number of chances, and you're not going to get the correct distribution. That you won't go to the different places in the correct proportion, okay? So if this proposal distribution here is not symmetric, then what ends up happening is that it's going to bias the distribution. So we have to assume that this is symmetric. That's a core assumption, okay? If we do that a core assumption, then what happens is that, we can show that here, let me see. Okay, so first of all, let me see, here are some notes. So this is just stating the thing in a little bit more detail. Okay, this is a different way of stating it. So you have an initial, this is the, it looks a little different, but this is exactly the same algorithm I described. You generate some proposal, W, W is the proposal. It's what I was calling X prime, okay? And it's according to some distribution Q, and the Q has to have that symmetry process. And then you accept or reject the proposal. So you calculate alpha, and that's the compute the acceptance probability. Now, okay, you'd say, well, what the heck is this expression here? So this is delta E, right? So if delta E is equal to U of X prime minus U of X. So this is new. This is proposed new state, right? So this is the change in the energy. If you take e to the minus delta E, right? If E is positive, this thing is going to be less than 1. If delta E is negative, that's going to be greater than 1. So if you take the minimum of this and 1, okay, and you set that to alpha, then when, if delta E is less than 1, then alpha is going to be equal to 1. Because then this thing is going to be greater than 1, and the minimum of 1 at this thing is going to be 1, right? If delta E is less than 1, right, it's, greater than 1. If it's greater than 1, then alpha is equal to e to the minus delta E. So that sort of simplifies the algorithm. Then I just say, oh, I accept with probability alpha. So with probability alpha, I accept W. And with probability 1 minus alpha, I accept X. Now, how do I actually implement this? I have to generate another independent random variable. And I compare that random variable. So I generate you generate U, and then what you do is you say, if U is less than alpha, less than or equal to alpha, accept, and if U is greater than or equal to alpha, reject. By reject, I mean I don't accept the proposal. I mean, this is rejecting, because I just leave the state alone, and that's accepting because I change the state. Now, what will happen here is that, okay, so now if you do this, it turns out that you can prove that this distribution is, it turns out, okay, first of all, facts. Facts. 1. Like X1, X2, X3, ... These X's are the states generated by this process that we're going to repeat of generating proposals and accepting or rejecting, okay? This sequence of states is, this thing is a Markov chain. Why is it a Markov chain? Well, it's a Markov chain because each new state depends on the old state and some random things, but it's not dependent upon 2 states earlier. So clearly it has to be a Markov chain because you can compute the next state from the previous state and some additional random information. Okay? So that makes it a Markov chain. What's not so obvious, and 2 is, it is a homogeneous Markov chain, right? It's a homogeneous Markov chain. What do I mean by homogeneous? I mean that the probability, the transition probabilities for the Markov chain are not a function of time. Well, that's true here because these rules I have don't depend on time. There's nothing in these rules which state that, there's no time dependence in these rules, right? well, I mean, the only time dependence, K is the time variable, but the only time dependence is through the indexing of the state itself, X. So it's a homogeneous Markov chain, okay? And let's see, so it's a homogeneous Markov chain. Now here's the really interesting thing. It's reversible. It's a reversible Markov chain. That's, at least not to me, very obvious. So to prove that it's reversible, we have to, 3, meets the detailed balance equations. Do you remember the detailed balance equations? The detailed balance equations mean that that for some distribution, and the distribution is going to be P of X, it means that for P of X times the probability of X prime given X is equal to P of X prime times the probability of X prime given X. That's the detailed balance equations. Because remember, the detailed balance equations said, another way of putting it was that pi sub I times Pij is equal to pi sub j times Pji. But the state here is X. And this might be confusing because we usually use I's and J's when we're talking about Markov chains. But X is a discrete state in this case. Well, we're going to assume it's a discrete state. And so it's like the index of pi here is like P, and Pij is like that conditional probability distribution, okay? So if we can show that this thing holds, then it solves the detailed balance equations. I haven't shown it yet, but I'm going to show it in just a minute. And since it solves the detailed balance equations, that means it solves the full balance equations, okay? And guess what? That means it's ergodic with stationary distribution P of X. Okay. But what's P of X? P of X is, remember, P of X is the thing we assumed, which is 1 over z times the exponential of minus u of x, where u is the energy, okay? So how do we prove this? 132, 133, okay. It's kind of interesting. It's true. How do we prove this? 130. Where's 131? Oh, here it is. Okay. Okay, here's the proof. So we need to show that so these are the detailed balance equations right there. So P of X we're assuming is 1 over z times the exponential of minus u of x, right? Because this is the desired distribution. By the way, this is known as a Gibbs distribution. Okay. So P of X is equal to that, okay? Okay, now we want to show that the detailed balance equations hold. They might not hold. If they don't hold, then everything I'm saying is not true. But it's going to turn out they do hold, but we need to show they hold. If we show they hold, then what does that mean? It means that it's a Markov chain, it's homogeneous. This is the detailed balance equation, so if that holds, it means that the detailed balance equations hold. If a Markov chain meets the detailed balance equations, what does that tell you about the Markov chains? It tells you that it's reversible, okay? It also tells you that the full bounce equations hold, and it tells you that whatever this function is that solved this detailed bounce equation, that it's the ergodic distribution of the stationary Markov chain, okay? Now, there's actually a few other things we needed if you go back. One is that you can get from any state to any other state, okay? So the probability of transition should be greater than, the probability of getting from one state to another in a finite number of steps has to be greater than 0, so that it's irreducible. And some different, and we have to show that it's aperiodic, and this number of states should be finite. But, you know, that's kind of a detail. We could show that for the particular cases, but this is the general situation, okay? So how do we prove that? Okay, now, okay, let's see if we can do this. Okay, now, if we start in state X, the probability of going to state X prime depends on two things. First of all, we have to generate X prime as a proposal. You can't get to that state if nobody proposes it. It's like you're trying to figure out where to go to dinner. If nobody says, well, let's go to pizza, you're not going to go to pizza. Okay, so someone has to propose going to get pizza. Okay, so someone has to propose X prime, right? And now, so someone has to propose it, and then it has to get accepted. So both things have to happen. It's not enough that you just propose it. You also have to accept it. You have to accept the proposal. So the product of those two probabilities is the probability of that transition occurring. So the proposal probability is X prime given X, and the acceptance probability is alpha of X prime given X. If you recall, I just wrote it down here, but I'll write it down again. I'll write it over here. Alpha of X prime given X is what? It's equal to the minimum. It's equal to the minimum of e to the minus delta e and 1, where delta e is equal to u of X prime minus u of X. Okay, right? So okay, now if we assume that if we assume that u of X, we're going to assume that u of X prime, we're going to assume that u of X prime is less than u of X. So assume u of X prime is less than or equal to u of X. So if that's the case, then this is 1. In that case, this equals 1. So, okay, now, okay, so now, this is by symmetry assumption. So we assume that these two things are equal. That was our assumption we made before, that this proposal distribution had to be symmetric. Okay, and now, okay, now the proposal, okay, now if I multiply this by, I can multiply by e to the, this is e to the delta x. Yeah, this is, well, hold on, now this is e to the delta x, and it's e to the minus delta x. So that's 1, right? So now this becomes, that's the, okay, right. If x is, oh God, this thing is gonna shut off. Okay. Okay, e to the minus u of x, this thing is the acceptance probability of, alpha if u of x is greater than u of x prime, then alpha of x given x prime is equal to the minimum of e to the minus u of x minus u of x prime and 1. And that, since this thing here is less than 1, that's just equal to e to the minus u of x minus u of x prime. Because we're assuming that the energy goes up, so this quantity here is less than 1. So that leads to this expression right here. So since these two things are equal, I can replace that. Now, the product of Q and alpha is exactly the transition probability. So I can replace the product of Q and alpha with P. So it's the probability of transitioning from x prime to x times e to the minus u of x prime, okay? Now, then if I bring the two expressions to the either side of the equation, okay, so now I have the expression that P of x prime given x is equal to P of x given x prime times e to the u of x minus u of x prime. So I can rewrite that, bringing the term over here that, P of x prime given x times e to the minus u of x is equal to P of x given x prime times e to the minus u of x prime. And then I can divide both sides by z. And then I've got that P of x prime given x times P of x is equal to P of x given x prime times P of x prime. Voila, it's miraculously true. I've shown the result. This is the detailed balance equations. Voila, it's amazing. You wouldn't think, but it's true. This is, I don't know, it's not totally obvious to me, but it turns out that this algorithm here, this is 30, oh yeah, this is 34, 33, okay. This algorithm forms a reversible Markov chain, and its ergodic distribution is nonetheless the miraculous, what did I just do with my pen? Okay, it's, the ergodic distribution is P of x equals 1 over z times e to the minus u of x. It's the Gibbs distribution. So we proved now that the Metropolis algorithm is a way, if you run it for long enough, it'll eventually converge to the desired distribution. Okay, so that's the idea of the Metropolis algorithm. Now, there's the problem with the Metropolis algorithm is that it's tricky because you have to generate. The problem is, what did I just do with my pen? Oh, here it is. Okay, problem. Might be difficult to find symmetric proposal distribution Q of x prime x, right? So it might be difficult to find a symmetric proposal distribution. So in certain cases, because, it's just sometimes it's tricky. So what if Q of x prime x is not symmetric? So what if it's not symmetric? So solution, a thing called Hastings or Metropolis Hastings Metropolis, I guess. Algorithm. So this works in a more general case where the distribution is symmetric. And there, the trick is that this expression for the acceptance probability gets a little more complicated. So in the standard Metropolis algorithm, you just have e to the minus this thing over here, right? And that's exactly what this is. I mean, here it's written as an exponential. There it's written as, as an exponent. So it looks a little different. But this part of it's the same. The problem with that is that acceptance probability is not going to work if you're always saying, well, let's go to pizza, let's go to pizza, let's go to pizza. You're going to end up going to pizza too often. So instead, what you have to do is you have to reject those things which get proposed too often, more often. You have to reject more often the things that get proposed too much. Okay, so so you have this additional ratio here. Okay, so let's look at that ratio. I feel like these fonts are kind of small. Let's look at that ratio. So that ratio says how often I project. So I'm in state X and I'm proposing state W. So this thing tells me how probable it would be to propose the state I'm in, given the state I'm proposing to go to. And this tells me that the probability of proposing W, given that I'm in state X. So our assumption was that these two things were this function was supposed to be symmetric. So under the Metropolis assumptions, this ratio would be 1. But this ratio captures the idea of how much you're over proposing certain transitions. And so this ratio then we use to penalize the acceptance rate. If you're proposing W way too much, then you divide by a larger number and you propose it and you accept it less. Okay? So if you use this allows you to then use any proposal distribution. Now the problem is this: if you use a really bad proposal distribution, what'll happen if you make crazy proposals? You say, let's fly to Venus. No. Let's jump off a building. No. I mean, you're just bad proposals. Of course, you're going to just reject them, and then nothing's going to change, or at least it'll change very, very slowly. So you really kind of intuitively like to make proposals that have a good chance of being accepted. On the other hand, you could always accept you can always make proposals which are very small perturbations in your current state. So if your current state only changes just a slight amount, then it's not likely the energy is going to change very much. But so you'll almost always accept it. But the problem is that the state's not changing very much. So you kind of need to strike a balance. You want to have a proposal distribution, and there's no formal theory, as far as I know, for this that says exactly what's optimal. But you want to pick a proposal distribution that changes the state, but doesn't change it so much that it's going to get rejected a lot. Okay. So it's kind of a tricky. It's a little bit like when you're actually writing proposals, like in research. You want an innovative idea, but not something so wacky that they're going to just say, well, forget that. That's silly, okay? Unless it's quantum computing. Then if you want to propose something really stupid, they'll fund it, okay? But for other fields, as a general rule, not so much, okay? So what happens then is that, so that's what you want to do here. Now, the Hastings Metropolis algorithm, 34, okay, 30, okay, 32, 31, 32, 33, 4, 35. Okay, now, okay, so now, there's some extensions of this. So this is then the proof. This is the proof that the Hastings Metropolis is also a reversible Markov chain. So this goes Hastings Metropolis. That's also detailed balance equations. It's reversible Markov chain. That means it's a full balance equations, and it's ergodic. And the asymptotic distribution is what? P of x equals 1 over z e to the minus u of x. That was way too small, but okay, you got the idea, hopefully. So that's the logic. You prove that the Hastings Metropolis algorithm solves the detailed balance equations. Then that means it's reversible, which means it has to solve the full balance equations. It means it's ergodic, and its ergodic distribution is whatever it used to solve this, which in this case is, let's see, this is 36, 37. So that's the stationary distribution of the ergodic Markov chain. Now, okay. Now what happens is that what you may do is, oh, we're out of time. Okay. Now you can, in the lab, x is actually equal to, say, r is in r to the n. Okay. And it might actually be, x might actually be in 0, 1 to the n. So this might be an Ising model. You do that in the lab. Oh, you didn't do that lab. I cut it out because there wasn't time. But so the image, actually, a better way to do it is like this. This is -1 + 1. So these might represent magnetic polarities. Okay, so it's like plus, minus, plus, like that, okay? Yeah, so you could represent them as black and white too. Black and white, like that. Actually, I think on the earlier section that we skipped, there's an example. This is from the earlier chapter on general Markov random fields. I think that's chapter 14. Is that correct? Yeah, so you have pluses and minuses, and the distribution, this can be used to model the distribution of thin materials that are magnetized. And so this was a really important problem that was considered around the Second World War, and amazingly they came up with some solutions to it. So you want to be able to generate samples from a distribution like this. We have local neighborhood interactions in a Markov random field that's discrete. And so now what ends up happening is that the state is actually is actually a high dimensional object, X. So the state is an image. So X, an image. It might be a binary image. So, so how do you work this? Okay, so now to do the Hastings Metropolis algorithm, it's a different strategy a little bit. So you have an image. So how does Hastings Metropolis? So Hastings Metropolis on image. So now the state X X1, but X is a member of, say, R to the N by M. So it's an image. And now you're going to do a proposal. And you're going to do an X2. Now, you could propose to change the entire image. But if you do that, then the probability of acceptance is going to be really low. So what you often do is just take one pixel and you just propose to change the one pixel in the image, okay? And then you accept, and now what will end up happening is the energy function, U of X, 1 here, and then there's U of X2. U of X only changes because that one pixel changes. So if you have a Markov random field, this is an MRF, then what ends up happening is it's only the local neighbors that affect the energy, okay? So what ends up happening is that U of X2 minus U of X1 is equal to whatever the local potential functions are, is going to be only a function of, say, V of X S, the pixel you're changing to, and X2 of delta S, that's its neighbors, minus V of XS1 and delta S1, right? So it's only local dependence. Okay, so I think we're over actually a little bit now. So, so we'll finish up, and then I think what will happen is that next time, maybe I'll go over a little bit more of this. And also come to me with any questions you may have that you'd like answers to, and I can also do that during these sessions. All right, so I'll turn off the recording at this time.